Thank you for watching the Data Center Storage Dilemma about scalability, durability, density, serviceability, and affordability. My name is Marc Staimer. I am the President and Chief Dragon Slayer of Dragon Slayer Consulting. I've been an analyst consultant for more than 18 years, and I have more than 36 years industry experience. I help vendors market more effectively, and end users I help solve their problems at no cost to them. I speak frequently at trade shows, and I also publish frequently with TechTarget. If you need to get a hold of me, if you'd like to chat with me, you see my email in the lower right, as well as my phone number and my Twitter handle. Going to cover a lot in this video, so stay tuned. There's a lot to go down, a lot to cover. We're going to talk about the mind-boggling digital data growth and the expanding gap between creating data and storing data. Legacy storage inadequacies and object storage solutions, as well as general object storage issues and how HGST Active Archive System solves those issues as well. To begin with, let's look at the mind-boggling digital data growth. Per Gartner, in the year 2020, we're going to create more than 50 zettabytes of new data. That's just in the year 2020. That's not accumulated, just in that year alone. And if you think about it over the past 2 years, again, per Gartner, 90% of all data ever created by mankind has occurred in the last 2 years. And that creation is accelerating. Most of that growth, though, is unstructured data, not structured. Unstructured are things like files and MP3s and videos, etc. Unstructured is where the growth is. It's 62% compounded annual growth rate. Structured are things that depend on a database, like email. And that's got a much lower growth rate of about 22% per year. Now, from the unstructured, there are essentially 9 different sources, which provides an overwhelming data variety. We're talking about machine logs and sensors, business applications, archives, media, analytics, documents, public web, and social media. But of those 9 different sources, the one growing the fastest is machine-generated data. And that means sensors and the Internet of Things and closed-circuit TV, logs, medical imaging, etc. That's growing at roughly 15 times the growth rate of human-generated data. And the files keep getting bigger. And I'll use video, film, and closed-circuit TV as an example. Per each hour recorded under 1080p, high definition, you're going to consume 179 gigabytes. That's a lot of storage for just 1 hour of recording. But wait, we're moving quickly now into 4K. 4K, and this is especially true of CCTV, 4K gives you much better resolution. So if you're doing video analytics, you need better resolution. Well, that takes about 38 times more storage than 1080p. 38 times more capacity. But it's getting worse. Not too far down the road, we're going to be at 8K within a couple of years. 8K takes 480 times more storage than 1080p. We're consuming more storage all the time. The files are getting bigger. And movies are a great example. Take a look at Avatar. It was a breakout movie in 2008. The finished movie was roughly about 1 petabyte. Several years later, we had the Hobbit movies, and the Hobbit movies were roughly about 35 petabytes each. Files keep getting bigger. And that's created a storage gap. What we're creating is bigger than what we can store economically or even physically in some cases. But that's a gap. And if we look at that gap, a lot of it comes from the IT budget shortfall. And the fact that traditional storage costs really aren't declining as fast as we're creating the data to store on them. So when you have this gap between what the budgets are and what the data is and the cost of storage, you're going to throw data away, and that's a problem. All that massive amount of data has value. How do we effectively and economically store it and archive it? How do you preserve it? How do you make it available and durable over time? The last thing you want to do is go seek out some data you stored, let's say 10 years ago, and find out it's just not readable. How do you serve it up for big data analytics and get actionable insight from it? Mine it for useful information. That's a real issue today. And traditional storage has issues with this, including the scalability aspect of it. Legacy storage was architected primarily for structured, not unstructured data. It's not designed to handle the massive amounts of unstructured data and the file sizes we're talking about. Controller performance has its limits as well, and data durability was dependent on RAID, the redundant array of independent disks. And there's a lot of labor intensity to legacy storage. You have a tech refresh every 3 to 5 years, which means a very manually labor-intensive data migration. And there's scale-out legacy storage issues as well. They have hard limits, scalability in nodes and capacity. Metadata restrictions, individual workload performance are all limited even in the scale-out. And data durability comes back to RAID again. Ultimately, you have inherent constraints on both types of legacy storage. And data durability, as I said, is a key issue besides scalability. RAID was never meant for big data. It was meant for dozens to hundreds of hard disk drives. It wasn't designed for thousands. And thousands of hard disk drives means that you're going to have several concurrent drive failures. Not one or two, but more than two. Because it comes from the same batch. And when they start to fail, more start to fail in a group than just one. And each failure increases to the probability of a next failure. Because you're exercising every single byte on every single drive when you're going through a rebuild process, which exacerbates the problem. So you have a higher probability of data loss, which means you're going to have to go through a process called recovery from other means like backups or snapshots or replicas, which is also time-consuming and labor-intensive. Candidly, RAID's just simply not enough for the size of the data we're talking about. And RAID rebuilds, let's be honest, take too long. When we measure disk drives in megabytes and even gigabytes, okay, we would rebuild in minutes or hours. But when we're measuring it in tens of terabytes, 10 terabytes or even 8 terabytes, you're looking at rebuild windows that can take days to weeks to even months, depending on whether or not you've set it as a background task, which most likely you probably will. And the reason you will is because it consumes too many cycles and resources from the storage controllers. And therefore, it takes longer to rebuild. And the longer it takes to rebuild, the higher the probability of another hard disk drive failure. And once you get past, let's say, RAID 6.2, you got a problem. You're going to deal with a data loss event and have to go through a recovery process. Object storage has become the prevailing answer, and for good reason. It can store and archive massive amounts of unstructured data. It can scale into the dozens to hundreds of petabytes, even exabytes or zettabytes. It provides a single storage pool, and the more nodes you add does not affect the performance because you don't have the messaging issues you find with things such as file systems. It supports multiple sites and has unmatched data durability and has extensive metadata, which means that you can mine it for analytics and actionable insights. And from an affordability point of view, it leverages commodity off-the-shelf hardware, keeping the cost down. It's a much lower cost form of storage. And the way that it handles that durability that I just mentioned is through the use of erasure coding. Erasure coding is much better than parity RAID. And the reason it uses something called width and breadth. So when you write the data, it breaks it up into chunks. Now, understand each chunk is actually an algorithm for the data, but it still breaks it up into multiple algorithms. And you don't have to read every one to read your data. So for example, let's say you go with a 12 by 9. That protects you against 3 concurrent failures. 12 chunks is your width, 9 is your breadth. That's how many you have to read your data. So when you get to your first 9, you read your data, they're all in agreement, great. If you don't get the next 3, you know you have a problem somewhere, so you write more chunks later using autonomous healing. But generally, it means you can set this up. It's selectable. Let's say you want to protect against 6 concurrent failures. You can do that. You can do a 16 by 10. Or you want to protect against 6 concurrent failures, but you don't want to have 60% additional storage. That's okay. You do a 26 by 20. The number of chunks increases latency in both writes and reads, but it increases the amount of data protection and durability of that data. Because when combined with autonomous healing, which is, again, what most object stores do, it looks at the data constantly, and if it finds a bad chunk, it just writes another one. There's never a rebuild, ever. But most object storage has other issues. There are two other significant issues. The first is eventual consistency. It's possible in many object stores in which you write a change to the data in one node while someone is accessing that same data from a different node. They could get an older version of the data, which would create an error. Now, HDST, Active Archive, and a few others have solved that so that you have immediate consistency. But not many of the object storage systems do that today. The bigger issue is storage density. Now, storage density is not scalability. In other words, the amount of capacity that you can manage under a single image. Storage density is the amount of capacity you have per rack unit. And the reason this is an issue is because data storage density in the data center has become a real problem. It's become a real cost problem. If you look at the studies for what it costs today, on average, for let's say a 5 to 10 rack data center, the total cost per year ranges from, for 5 racks, roughly under 100,000 to just under 171,000 for 10 racks. So if you look on a per rack basis, that's roughly approximately 20,000 to 17,000 per rack, or 17 to 20, depending on the number. And realize that it includes cost to build, to maintain, labor costs, a variety of other aspects. If you look at it from a cloud point of view, infrastructure as a service, or even a colo, for the 5 to 10 rack system, you're looking at 12 to 24,000 per rack. And again, those approximates are varied by power density, design, maintenance, cage space, cross connects, bandwidth, VPNs, etc. More of the same. Now, how most object storage offerings deal with the density issue? Generally, capacity is tied to server nodes. And they're small nodes, typically about 2U, in which you have roughly 12 3.5-inch hard disk drive slots. There are some that are bigger and some that are smaller, but generally this is about what it works out to be. Now, some also utilize high-density enclosures. Typically, you're going to have up to 60 drives in a 4U. And these are the 3.5-inch 8 and 10 terabyte or 6 terabyte drives, and up to 90 in some cases in 4 rack units. Let's look at each one of these and the pros and cons. For the standard type of object storage hard disk drive node enclosure, it's simple. You can access the hard disk drives from the front, so you don't need any special equipment. You don't need any ladders. Drive has a problem. You take the drive out, you put a new one in. That's all you do. It scales processing and capacity together, so you have never going to reach a situation where you run out of performance before you run out of capacity or vice versa. So it scales them both together. That's the good. The bad, and there's always bad, the bad is there are lots of nodes to manage. More processing than required. It's a relatively low density per rack. It hogs rack space, and it adds a lot of unnecessary costs in not just the nodes, but in the supporting infrastructure. You have more cables, more connections, more transceivers, more switches, more switch ports, more core switches, as well as the leaf switches. It can get pretty ugly in the infrastructure costs as well. So generally, object storage general hard disk drive node enclosures are easy to service, simple to scale, but they consume too much rack space. They consume too much supporting infrastructure, and they add too much cost. What about the high density hard disk drive enclosures? Well, the pros here is that they reduce rack unit consumption. Their supporting infrastructure is going to be reduced, and the cost is going to be reduced. That's why they're high density, so less RUs. But the cons, all the access is from above. Not from the front, from above. You gotta open the top. And to open the top, you gotta pull them out. And you need a ladder to get from the top. And the problem about pulling them out on these little rails is they weigh typically more than 300 pounds. Not many administrators can hold up 300 pounds with one hand, and don't expect those rails to be able to support that when you bring it out, they were changed out of drive. It's not going to happen. They're going to break off. It's a good way to lose a foot. So you can't just slide that drawer out. You're going to need a hydraulic lift. In a hydraulic lift, there's really never enough of them, and they're always unavailable when needed. They're never where you want them to be. They're costly. So overall, these two factors are going to reduce the savings you get from having high density. So the object storage high density hard disk drive enclosures solve the density problem, some of the cost problems, but they create serviceability and other cost problems. So not a perfect solution. This is where the HGST active archive system comes into play. It uniquely solves all the object storage issues we've discussed and these other issues that are created by object storage. Scalability, data durability, consistency, density, serviceability, and affordability. On the scalability side, it scales up to 6 racks of 42U each. Local or in a 3 geo-node cluster, in other words, distributed geographically. And per 42U racks, it ranges from 4.7 petabytes raw of 8 terabyte drives to 5.88 petabytes raw with 10 terabyte drives. 6 racks, and that's based on what's been tested to date. That's not a theoretical limitation. That's just a testing limitation. Means that you range from 28 roughly petabytes raw to more than 35 petabytes raw in 6 racks. That's a lot of capacity in a very small space. On the durability side, HGST has its own special form of erasure coding called bit spread. Objects are spread as wide as possible, the width and breadth selectable, as I mentioned earlier. And what's kind of unique about it is the spreading is hierarchy aware. It's aware of where it is. And that enables even higher durability. Let me give you an example. Let's say you have a 4% annual drive rate failure, which is a relatively low drive rate failure, by the way. But let's say in these thousands of drive or hundreds of drives, you have a 4% annual drive rate failure. The HGST active archive system is going to maintain a very high 10 to the 16th data durability. That's higher than a drive by itself, by orders of magnitude. And the HGST active archive system deals with consistency by providing immediate consistency. It doesn't allow reads of old, non-updated objects until all the nodes are updated. On density, it's got the highest density enclosures on the market. It's not 60 drives per 4U or 90 or 84. It's 98 helium hard disk drives per 4RU enclosure. That means it's 784 terabytes to 980 terabytes raw, depending if it's 8 terabyte or 10 terabyte helium drives. Now, what makes this unique, and this is unique, is the serviceability of these high density enclosures. There are no large drawers to pull out. There's no high weight that you've got to support with a hydraulic lift. Because each enclosure is broken out into 7 sleds of 14 drives each. And you just have to slide the sled out from the front, not the top, from the front. It's simple, it's fast, it's easy to get access to the drives. So serviceability is a huge advantage. That makes it very affordable. Very low cost to acquire. You can start as small as 672 terabytes raw. And to scale, it's very simple to add more enclosures, more processing units. And to operate, it consumes minimal rack and floor space. It consumes minimal supporting infrastructure as a result. This gives you the best-in-class serviceability and intuitive manageability. So in summary, and to conclude, solving big data storage, explosion, scalability, durability, and affordability issues requires moving away from legacy storage and using object storage. And object storage will solve those issues. But the other issues it introduces, such as eventual consistency and density and serviceability and limited affordability, are solved by the HGST active archive system, which solves both the object storage issues as well as the legacy storage issues. And it does so in a unique manner. Thank you for watching this video. And if you want more information, please go to www.hgst.com/products/systems/HGST-active-archive-system. Thank you again.